Check it out now, y'all.
NanoHub U, online instruction.
Well, in this lecture, we'd like to sort of wrap up our discussion of special relativity, and we'd like to do that by discussing relativistic energy and try to explain to you what happens to the energy of a particle as its velocity approaches the speed of light. So, as you probably can imagine, this concept of relativity makes us rethink energy. And in particular, I like to focus on the kinetic energy here because it's a quantity that we've used many times in a classical context. We like to see how the kinetic energy of an object changes as its speed increases toward the speed of light. So to motivate that discussion, I'd just like you to think about a block that's moved between a position x0 and a position x1. The block is moved by the application of a force. Initially, the block is at rest, so its kinetic energy is equal to 0. Because its kinetic energy is equal to 0, its velocity is equal to 0. After we push the block through this distance, right, the block then acquires a velocity u, and we say that it has a kinetic energy k sub f, which is its final kinetic energy. And of course, classically, we know that kinetic energy is 1/2 mu squared. So how is this quantity called kinetic energy formally calculated? Right. So if you recall way back to the beginning of the course, first week of lectures, we mentioned something called the work energy theorem. And the work energy theorem just basically said, if you tell me the net work that you did in moving the block from x0 to x1, right, that net work is going to show up as a change in the kinetic energy of the object. And so if the initial kinetic energy is equal to 0, then the work done is equal to the final kinetic energy of the object. And if you want to formally calculate this kinetic energy change by the work dW that you have to do, right? Well, the way you do that is if you know the force is a function of position, you have to integrate f dx from some initial position x0 to some final position x1. And so this integral requires you to know f as a function of position x. If you don't know f as a function of position x, well, then you can't do this integral and you can't calculate the kinetic energy. So what happens if you, for instance, happen to know the velocity is a function of momentum rather than the force is a function of x? Can you also calculate the kinetic energy of the object? And the answer is yes. And I review some of the important results over here using the chain rule for differential calculus. The reason you can calculate the kinetic energy by integrating the velocity as a function of momentum is because the change because the work done is equal to v times dp, right? And so that can be proved just by working through this simple line of arguments here. And so if you happen to know the velocity as a function of the momentum of the particle, then you can integrate it from its initial value. The initial value of the momentum is 0 to its final value p, and that also gives you an expression for the kinetic energy. All right? So this is a completely general discussion, right? You depending on what you know, right, which you've measured experimentally, you can express this change in kinetic energy in different ways. So the third way I do it is if you happen to know the work that you put into the object is a function of the velocity, again, you have to work through this chain rule argument here, but eventually you can calculate the change in the kinetic energy if you know the momentum is a function of velocity, right? That's the bottom line. So, of course, classically, right, just let me remind you that the change in momentum is equal to the mass times the change in the velocity. So if you, for instance, put this result into this equation, right? It's a pretty simple matter to do the integration, and you find out that the kinetic energy is equal to 1/2 mu squared, which is exactly what you would expect, right? Now, what happens if the momentum is going to be described by this relativistic equation, right? This is the result that we had obtained at the end of the previous lecture. What happens to the kinetic energy? Well, what we have to do is we again have to go back to this equation and we have to evaluate it. We have to evaluate v dp, where now dp is going to be a relativistic momentum, and we have to integrate that from some zero value to some final value, and that'll then give us an expression for the kinetic energy K of the object that's being moved. So I just worked that out in this example, right, on this slide. What we're going to need to know is we're going to need to know an expression for dp using the relativistic definition of momentum. And so what we have to do is we have to take the derivative of the momentum defined this way with respect to the velocity v, and I work out the arithmetic in the appendix. So please go and look at the appendix, and you'll find out that dp dv is just equal to this quantity m0. So m0 is the mass of the object when it's at rest, times this quantity 1 minus beta squared to the 3/2 power, right? So the kinetic energy K can be calculated by integrating V times dP, where dP is gotten from this expression. And this is a standard integral. You can look it up, and what you find out is that you can evaluate it. And at the end of the day, you find out that the kinetic energy relativistically is going to be equal to the quantity gamma minus 1 times this value m0 times c squared. Right, so that is the new definition for kinetic energy. It's valid for any velocity that the object has. Of course, as the velocity of the object gets smaller and smaller, you go to the non-relativistic limit, right? So if you want to see how this expression reduces down to the standard 1/2 mv squared result, check out the appendix, because I work out the arithmetic and I evaluate this expression in the limit when v gets smaller and smaller. So it reduces down to the classic limit. It's interesting to plot the relativistic kinetic energy as a function of v over c, right? So again, and I compare that to the classical expectation here. So classically, the kinetic energy would be equal to 1/2 mv squared. Classically, there's no limit on the velocity of an object, so v can be greater than c. And if you plot the classical result, you would end up with an expression that looks like this, or a plot or a line that looks like this. If you plot the relativistic kinetic energy, you can see that there's a huge discrepancy between the relativistic kinetic energy and the classical result when v is roughly greater than 0.5 or 0.6 c, right? The discrepancy increases the closer you get to the speed of light, right? So this is the relativistic expression for the kinetic energy. It's gamma minus 1 times mc squared, where m is the rest energy of the object that you're considering. So what I like to do is I like to try to solidify these concepts of momentum and kinetic energy by just considering a proton, which has a speed that's 0.866 times the speed of light. And I'd like to ask you what the momentum of that proton is, and I'd like to ask you what the proton's kinetic energy is. So if you have not listened to the previous lecture or this lecture, you might think that the momentum of the proton is just going to be given by m times v, right? And I know what the speed of the proton is. It's 0.866 times the speed of light. I can look up the mass of the proton, and I can just multiply those numbers together and I get a number. In this case, it's about 4.3 times 10 to the minus 19 kilograms meters per second. That is a wrong calculation, right? It's incorrect because it very clearly the velocity of the object is moving comparable to the speed of light. You can't use the classical result anymore. What you have to do is you have to resort to a relativistic calculation. And whenever you do a relativistic calculation, you first have to evaluate this quantity gamma. So for the case of v equal to 0.866 times the speed of light, turns out gamma is precisely equal to 2. And so now the momentum of the particle, the relativistic momentum of the particle, is just going to be twice that which you expected classically. And that factor of 2, of course, just comes out from evaluating the additional factor of gamma that multiplies the classical momentum. So this is the correct result for the momentum whenever a particle is moving close to the speed of light. A comparable discussion can be offered by asking what is the kinetic energy of this proton, right? So again, if you haven't listened to the previous lecture, if you haven't listened to this lecture, you might say, oh, the kinetic energy is just p squared over 2m. I've already calculated p incorrectly up here, so let's compound the mistake and use it in this expression. You calculate p squared over 2m, and you would say that the kinetic energy is 5.5 times 10 to the minus 11 joules. That is an incorrect result because it uses the classical equations. Instead, what you have to do is you have to use the relativistic expression for kinetic energy. So you have to take gamma minus 1. You have to multiply it by the mass of the proton when the proton is at rest. That's m0. And then you have to multiply that by c squared. And what you find out is that the kinetic energy of that proton is really 1.5 times 10 to the minus 10 joules. So just being able to calculate these simple quantities using the correct formula that incorporates relativistic effects, that demonstrates some understanding of the topic material, and it indicates that you have some core level competency in solving these problems. So you have to be able to do these simple calculations correctly. It's an important part of the course, right? So if I had to summarize some of the important results here that we've covered, I'd like to introduce the concept of something called the total energy, right? The total energy is going to be a combination of the kinetic energy of the particle K plus its rest mass energy, which is defined to be m0 c squared, where m0 is the rest mass of the object in question, right? And by adding the rest mass energy to the kinetic energy K, we define a new parameter which is referred to as the total energy of the particle. And by very simple arithmetic, the total energy of the particle is now equal to gamma m0 times c squared. We've already defined a relativistic momentum by incorporating this additional factor of gamma into the discussion. So you take the classical momentum and multiply it by gamma, that gives you the relativistic momentum. And the last important concept here is that this total energy E, right, equals this rest mass energy m0 c squared when the velocity of the particle or the object goes to 0. So when the velocity goes to 0, then gamma is equal to 1, right? When gamma is equal to 1, this term, the kinetic energy term, drops out of the total energy. And what this equation then says is that the energy of the particle is equal to m0 c squared, right? And this is referred to as the rest energy of a particle, and this is, of course, Einstein's famous equation, E equals mc squared, and it basically says that a particle with a mass has an energy associated with it, just even when it's sitting stationary. So that's an important concept, and it comes out of this discussion of relativistic energies in a pretty straightforward way. It's useful to consider the what's called the energy momentum relationship for relativistic particles. And by that I mean we've got an expression for momentum and we've got an expression for energy, right? The momentum, the relativistic momentum is this gamma m0 times v. The total energy of a particle moving at speeds comparable to the speed of light is this gamma m naught c squared. So the question is there a relationship between momentum and energy that's easy to write down? And the answer is yes, there is. There's a few lines of algebra that are required, and I work through that here. Basically, what you do is you end up writing an expression for the energy squared, and when you write that expression for the energy squared, you find out that there's an additional term in that expression for E squared that involves the momentum squared, P. That's this quantity P squared. So please look through the arithmetic. It shows you how to go from E squared down to this very famous equation, which says that the total energy of a particle E squared is equal to the square of its rest mass energy, m0 squared c to the fourth, plus P squared c squared. And this then, of course, is the relationship that we wanted. We wanted an expression between E, total energy E, and a momentum P. And this is the equation that gives you that relationship. It's often written in terms of, by taking the square root of both sides of this equation. It's often written in this form. And it's extremely important if you're dealing with objects that move comparable to the speed of light. So it's an important result. So I'd like to try to illustrate that by just doing a simple calculation. And as always, the arithmetic in this is pretty straightforward. It's just you have to be able to apply the correct equation in the correct circumstance to calculate the quantity that's being asked for. So in this example, I've got an electron, and I say that electron is moving at 0.99 times the speed of light, and I want to know what's the rest energy of that electron. I want to know what its total energy is, I want to know what its kinetic energy is, and I want to know what its momentum is. So hopefully what you recognize immediately is that the velocity is comparable to the speed of light. So when you evaluate these quantities, you have to use the relativistic results that we've derived in the previous slides. So the definition of the rest energy is just the mass of the electron times the speed of light squared. That's Einstein's E equals mc squared equation. And I just worked through that example here in some detail. You can get the answer either in joules or in electron volts, and it's very convenient to represent this quantity in electron volts in terms of million electron volts, which is this capital M EV here. So this capital MEV is equivalent to 1 times 10 to the 6th electron volts. But the quantity that you can remember is that the rest energy of an electron is 0.511 MeV, and you can use that number to greatly simplify a lot of the calculations that involve total energies, kinetic energies, and relativistic momentums. And so one of the key ideas expressed in this slide is that once you know this rest energy, all these other quantities can be calculated in a pretty straightforward way, okay? And hopefully that's a message that you take home from this lecture. So for instance, if you want the total energy of this electron, the total energy is defined relativistically as gamma mc squared. I've got to calculate gamma, and for an object moving at 0.99 the speed of light, turns out gamma is about 7.09, 7.088, right? So I have to use that expression down here, and I find that the total energy of that particle is equal to 3.622 million electron volts. I can ask, of that total energy, how much of it is kinetic? Right? The kinetic energy, relativistically, is this gamma minus 1 times the rest energy, m naught c squared. But we've already calculated the rest energy. It's 0.511 million electron volts. So it's pretty simple to take the value for gamma, subtract 1 from it, multiply it by the rest energy of an electron, and immediately you can tell that the kinetic energy of this electron is going to be 3.11 million electron volts. And then the final result is calculate the relativistic momentum. So what I encourage you is don't go through the calculation where you have to evaluate the velocity of the particle explicitly. Instead, spend a few minutes doing some algebra here. What you find is that you can write this relativistic momentum in terms of the ratio of beta over c times the total energy E of the particle, right? And it's always the case, seems to be always the case with these relativistic calculations, that if you just spend a few minutes of algebra, you can write down the answer in a transparent form that does not involve evaluation of some god-awful set of fundamental constants. So here, right, beta is known, beta is 0.99. We have to divide by the speed of light c, and then we have to use the total energy E that we've already calculated. So what we find that the momentum is given by 3.586 million electron volts divided by c. So it's also common practice when you express momentums for relativistic particles to express the momentum in terms of electron volts divided by the speed of light. So you don't even make the effort to cancel out or to evaluate the speed of light in this expression unless somebody really wants to know what the momentum is in terms of kilograms meters per second. More often than not, this new set of units where the momentum is equal to a million electron volts divided by the speed of light c is used. Now the reason that quantity is useful is because if you're going to check, for instance, and just say, well, I've calculated each of these quantities separately, when I add them up, do I satisfy this momentum energy relationship for relativistic particles? And so the point is we've already calculated the total energy of this electron on the previous slide. We've already calculated the rest energy of the electron on the previous slide. And we've got the momentum in terms of units of c also on the previous slide. But when you multiply p squared times c squared, you can see that this factor of c squared is going to drop out. And so you're left with a very simple equation that you can evaluate on a calculator, very little algebra involved. And what you find is that to within the round off error, the calculation, the calculation of the total energy, the rest energy, and the momentum in separate calculations does satisfy this energy momentum relationship, which shouldn't surprise you because it's a correct result that's used over and over again in relativistic kinematics. So, I just want to make the point that this new system of units in which mass is measured in terms of MeVs over c squareds, momentum is measured in terms of MeVs divided by the speed of light c. I've got a discussion about those new set of units in the appendix, and I encourage you to take a look at that and make sure you understand the ideas involved there, because being able to do these calculations quickly and accurately is important. And these new set of units for masses and momentums are a key point to enabling that simple calculation. Just want to mention that there's a very elegant connection between this energy-momentum relationship for relativistic particles. And the idea is that you can recognize that this energy-momentum relationship, the form of the energy-momentum relationship suggests a triangle, because here you've got E squared, here you've got P times C quantity squared, and here you've got the rest mass energy squared, right? And so these two quantities can be the legs of a right triangle. This would then be the hypotenuse. And so what you end up with is you end up with a triangle that looks like this. The base of the triangle is the rest mass energy of the particle, m0c squared. So when I tell you what a particle is, and I tell you what its rest mass is, that sets this angle here. The momentum of the particle, the relativistic momentum of the particle, sets this leg of the triangle here. And the total energy E of the particle is then the hypotenuse. And you can see that hypotenuse is made up of two contributions. One is the rest mass energy, m0c squared. And then this little bit here has got to be the kinetic energy in order to satisfy this equation. What angle theta is this right triangle defined to be? Well, it turns out, I show the arithmetic at the top. The sine of this angle theta has got to just be equal to beta, where beta is the ratio of V over C. So this is a very simple geometric relationship that I find very helpful sometimes when I'm trying to evaluate this expression, because it allows me to see what the rest mass energy is compared to the kinetic energy K of the particle. And it allows you, in some circumstances, to be able to estimate the relativistic momentum just using simple trig. So I'm running out of time. I got to stop. I'll just say I've put in a couple of examples in this lecture to illustrate some of these ideas. One of the examples is to calculate the relativistic de Broglie wavelength of a particle. So I go back and I ask, how do these ideas about relativistic kinetic energy and relativistic momentum, how do those ideas affect our estimate of the de Broglie wavelength, which is, of course, something that we discussed very early on in the semester. And then I also have another example where I take the energy momentum relationship for relativistic particles, and I discuss it for the case of photons. So for the case of photons, photon has zero mass, right? And then you're left with a very simple relationship that takes you all the way back to the first week of the semester between energy and momentum of a photon. So that's also discussed in one of the slides, and I encourage you to take a look at that when you get a chance. Next week we're actually going to derive Compton's formula. So we're going to go back to the beginning. We're going to close that loophole, because when we first discussed Compton scattering, I just wrote down Compton's formula, and I made a vague promise that we'd come back to that formula once we understood a little bit about relativistic kinematics. So now we understand relativistic kinematics, so we can now derive Compton's formula, and I'd like to do that next week to start the week off. So that'll be the first lecture for the next week, next set of lectures. So that's all I got to say. Just a few more lectures on relativity, and then we're going to move into a short segment about nuclear physics and talk a little bit about the physics of the nucleus. So we'll see you next week, and thanks for listening to this discussion about relativistic energies.